Good morning, students. So today we are discuss about different numericals which are came on two-phase heat transfer process. So let us start the numericals. So first numerical is a horizontal copper wire is submerged in water at 8 bar. It carry it carry a current of 125 ampere with and a voltage of 2.2 volt is applied to it. If the surface temperature of wire is maintained at 200 degrees Celsius, calculate the heat flux, boiling heat transfer coefficient for it. Take dimension of wire is 1.25 mm diameter and 25 centimeter long. So what we have to do? First we have to write the given data. Means current is 125 ampere, then voltage is 2.2 volt, pressure is 7 bar, and the temperature of wire is 200 degrees Celsius. And the diameter of wire is 1.25 mm. So we are converting into the meter. It is equal to 1.25 into 10 to the power minus 3 meter. And the length of wire is 25 centimeter. That means 0.25 meter. So what we have to find? First of all, heat flux, then boiling heat transfer coefficient H. So we all know that uh, power is equal to electrical energy, or say power is equal to V into I. So first we are multiply V into I. So we are getting 275 watt, and the surface area of wire is IDM. So we are getting 9.8 into 10 to the power minus 4 meters square. So according to according to the formula, heat flux is equal to rate of heat transfer per unit area, that gives 280.33 kilowatt per meter square. This is our heat flux. At the same time, secondly, we have to find the heat transfer coefficient H. So at 7 bar pressure, the saturated temperature of water is 165 degrees Celsius. It is came from the steam tower. So Q is equal to H into A into delta T. We have already Q, A and delta T. So we are easily find out the heat transfer coefficient of the wire. The heat transfer coefficient of the um, heated boiling water. The second question is nickel wire is submerged in a pool of water part. The part is open to atmosphere. The diameter of the wire is 1 mm and the length of wire is 0.2 meter. The current of 190 ampere is passed through the wire at the burn out point. Calculate the voltage at the point, at that point. So density of that fluid is equal to 0.595 kg per meter square, and sigma is equal to 58.9 into 10 to the power minus 3 Newton per meter. So with the help of first, we have to write the given data. B is equal to 1 mm, or 1 into 10 to the power minus 3 meter, and length is equal to 0.2 meter. So uh, we have we have to calculate all, means they are not providing the pressure. So we are just assuming that it was working with 1 atmospheric pressure, and at burn out point I is equal to 190 ampere, and volt, we have to find out the voltage. So at 1.013 bar pressure and 100 degrees Celsius evaporated water in the steam table, we are getting the density of 57.9 kg per meter square. The density of fluid or vapor is 0.595, which was already given in the question, and sigma is equal to 58.9 into 10 to the power minus 3 meter. Similarly, enthalpy of fluid to gas is 22, 2257 kJ per kg. So, so rate of heat transfer is actually find out the formula 0.18 into density of vapor raised to power 1 by 2 into hfg into sigma into rho L minus rho V into G raised to power 1 by 4. So ultimately we have found out the rate of heat transfer. It is Q, and ultimately total heat is equal to the rate of heat transfer into its surface area. So multiply by surface area pi g L. So we are getting 1087 watt, and ultimately Q rate of heat transfer is equal to V into I. I think it was done use this type of formula are using in the um, experiment. So you are getting the voltage V is equal to Q upon I. So 5.7472. Similarly, the third question came. A copper pan of 35 centimeter diameter is maintained at 115 degrees Celsius. Water is boiled in the pan 20 atmosphere. Calculate the heat transfer by timer. And second, rate of evaporation. And third one is a critical heat flux. By using this correlation, we have already derived this equation in the previous lectures. So as per the given data, diameter is 35 centimeter means 0.35 meter. T saturated is equal to 115 degrees Celsius, and sorry, T superheated is equal to 115 degrees Celsius, and T saturated is 100 degrees Celsius. So thermophysical properties of water at table A2 at 100 degrees Celsius, we are getting RL means density of fluid is equal to 958.4 kg per meter cube. Density of water, vapor is equal to 0.5955 kg per meter cube. And density of, sorry, specific heat of that liquid is equal to 4220 joule per kg Kelvin. And mu is equal mu of this liquid and the fuel is equal to 279 into 10 raised to the power minus 6 newtons per meter square. It was already given in your notebook. So ultimately we have find out and the pressure of that liquid is 1.75 and enthalpy is 2257 kilojoule per kg, and sigma is equal to 58.9 into 10 raised to the power minus 3 newton per meter. So from the steam table with 1 atmospheric pressure, T saturated is equal to 100 degrees Celsius, and enthalpy of that fluid is 2257. So the excess temperature is 115 minus 100 is equal to 15 degrees Celsius, and it get delta TP. So heat supply by the burner, we have to, I think we have already gives the formula Qs is equal to this one. So we are just putting the values in this one and calculated. It was getting 461.06 kilowatt per meter square. Similarly, the boiling heat transfer coefficient is given by Q is equal to 461, means it is the value of Q and the surface area. So, in that case, therefore d square we are getting the total heat transfer, and when we are multiply this total heat transfer with mass flow rate and enthalpy, then we are getting the mass flow rate, and it was 70.75 kg per hour. And ultimately critical heat flux, we are getting this equation from the previous lecture. So QC is equal to this one, and when we are putting these values in this equation, we are getting the 1.5206 megawatt per meter square. Similarly, we have to attain this numerical. A horizontal heated element is maintained at 260 degrees Celsius. The diameter of element is 5 mm and the emissivity of the surface is 0.9. Calculate the heat transfer unit length of element. So we have the property of water, which is equal to 98.4 kg per meter cube, and enthalpy of latent heat or say enthalpy of fluid to gas is 2257. And also we have the properties of water. So UV is equal to 4.807 kg per meter cube, Cp is equal to 2.56 kilo joule per kg Kelvin, and thermal conductivity of 0.0331 watt per meter Kelvin, and mu is equal to 14.85 into 10 raised to the power minus 6 Newton second per meter square. And H convective heat transfer coefficient, we have to use this equation. So first of all, we have to put the given data. Then after we have to calculate the desaturated value at 1 atmospheric pressure, because the pressure is not given. So it is 100 degrees Celsius. So the excess temperature is 260 minus 100 degrees Celsius. It is get 160 degrees Celsius. So from theory we have to say that film pool boiling condition exists. So as will we as well as epsilon is given by, so the radiation is also considered. So H it was for when we are considered radiation and heat transfer coefficient, then we are getting H convective plus 3 by 4th of H of radiative. So we have the equation, which we already have the equation in the question. So first we have to find out the convective heat transfer coefficient. Then after this convective heat transfer, we have to find out the convective heat transfer. Then after we have to find out the rate of heat transfer on the radiation basis. So H radiation into desaturated superheated minus desaturated, or say sigma into epsilon into T as super fourth power of uh, fourth power of temperature at the superheated, and the fourth power of temperature at the saturated. So in by this equation, we have to find out the radiative heat transfer coefficient, that is 14.57 watt per meter square Kelvin, and ultimately find out the thermal heat transfer coefficient. So we have to just put convective heat transfer coefficient plus radiative heat transfer coefficient in this equation, and we are getting 458.41 watt per meter square Kelvin, and ultimately heat dissipated per unit length Q is equal to H into A into delta T. So we are getting the heat dissipation per unit. Okay. So let's start with new topic. It is called condensation. Condensation means when condensation is a reverse of boiling process because just